Okay, we might as well get started. So I've already told you, the other great revolution of the 20th century, the first one being relativity. Einstein changes everything, and he points out that motion is relative. It's done in 1905, that this observer and this observer moving relative to each other has to get the same laws of physics. And after his insight, all the laws of physics that follow have to be relativistically invariant. So what these guys who are going to develop quantum mechanics must do is make sure that quantum mechanics is also relativistically invariant. That is the other great revolution. And since so many people are involved and such a tremendous change in the way people think takes place, it's going to take us three periods to get all the way through to the time when quantum mechanics is correctly and fully established. Now, since Copernicus, the word revolution in a scientific context really means a change in how we think. There's this huge change in things that takes place in roughly 30 years. Now, as far as quantum mechanics goes, a lot of people say a lot more happens in the next 40 years after 1930. And indeed it does, but it gets into things like quantum chromodynamics and quark theory and a whole bunch of stuff that's extensions of this way of thinking. And so I'm really only going to take you contextually through to roughly into the 1930s, when the fundamental body of quantum mechanics is in place. Because the rest of that stuff builds off this. It doesn't have to generate a completely new thought process. It's just a more complicated thought process as you go on in time. And the two revolutions, of course, are relativity and quantum mechanics. We're going to be talking about a whole bunch of people. The first group in black, they're the guys who dealt with black body radiation, so they left their names in black. Stefan Boltzmann, Wien, Rayleigh, and Jeans all contributed information to the subject of black body radiation, which is one of the things that classical physics could not properly understand. Classical physics gave various experimental results and some analysis, but couldn't really explain black body radiation. Does everybody know what black body radiation is? Okay, if you don't, we're going to look at it in a moment. And these other guys introduced something into physics that is at first and at last even very distressing. They introduced the idea of, anybody want to guess? The quantum, integers, 1, 2, 3, 4, integers, as describing the states of atoms. Now that's unheard of prior to this. And it's an incredibly radical way of thinking about things. In fact, Max Planck quantizes light, which for the previous 97 years, since Thomas Young's experiments, has been thought to be proven without a doubt to be a wave. And since Maxwell's theory, we know it's a wave. It's got the beautiful wave equation, and it's polarized, and it propagates, does all that stuff. Mm-hmm. But Planck introduces quantization of waves. Anyway, the problems that physics faced are listed here. There's some nagging problems in classical physics. Black body spectrum, line spectra of atoms, and the very fact that atoms are stable. We don't sit here and watch things decay and go away. You know, the table's not going to vanish while we're sitting here. Classical physics could not explain that. Classically, there's no reason in classical physics why things don't go away. Well, here's the black body curves. They have this beautiful shape. This is measured in wavelength, so that's the infrared going that way, that's the ultraviolet going this way. And there's a peak that with temperature moves to shorter wavelength. And the power radiated, of course, goes up with temperature. You know, you've seen hot items like your stove element. As you turn up the height from low to hot, higher and higher on your stove element, if that's the kind of stove you have. And all of that is very interesting, but not explainable in classical terms. And this is even more weird. This is the spectrum of hydrogen. And of course it's compressed. It's showing from 100 nanometers to 10,000 nanometers, and it's a very strange presentation. But just look here in the visible. The hydrogen spectrum is a series of lines. 1, 2, 3, 4, and then it gets kind of clustered together in what almost looks like a continuum. We're going to see where all that comes from. And there's groups of lines. This group here, this group, this group, this group, and so on and so forth. And that is completely unexplainable in classical terms. Where do those lines come from? And by the way, the word line is a result of how people do spectroscopy. So we'll talk about that as part of this discussion. And so since we're going to talk about spectra, it's worth a few minutes talking about how do you do spectroscopy.
Excuse me?
Yes.
Did people observe the line spectra before the quantum mechanics?
Oh, yes.
Yeah.
Yes, very definitely. And here's where we're going to talk about it. As soon as people had prisms, back in Newton's days, they observed that the sunlight could be broken up into colors. That's spectroscopy right there. And one of the things that Newton did was take another prism and try to put one of the colors back together and get white light, and of course he couldn't. And he played with prisms and tried to do various things with the different colors. Thomas Young, when he did his two-slit experiment and saw that light was wave-like, realized that if he had more than two slits, he could make more higher resolution separation of the light into more highly resolved colors. And he invented the grating.
Yeah.
So in the 1800s, people actually began to do better and better spectroscopy. One of the easiest things that they did, one of the most obvious things to do, was to look at the sun with either a prism spectrometer or a grating spectrometer. And what they saw was a black body spectrum with various missing lines in the spectrum.
From the light of the sun?
Yes. If you did that today, you would see missing lines in the solar spectrum, which turn out to be absorption features in the gases that surround the sun, that are out at the higher
So that
levels.
time they were not trying to observe things in our
Oh, wait, I'm
molecule
sorry,
scale.
please, ask your questions. I forgot.
So that time people find the line spectra from the sun instead of particles in the molecule scale.
Well, the gases around the sun are so hot that they're all atomic. If they're not plasmas, they're atomic gases, depending on how far out from the surface they are. But what was observed of the solar spectrum in the kind of middle 1800s was what turns out to be the absorption spectra of gases around the surface of the sun, which again could not be explained by classical physics.
How did they distinguish those between the atmospheric absorption lines?
You mean the atmospheric absorption lines here on the Earth?
Mm-hmm.
Eventually, experimental observations of various gases on the Earth confirmed that those lines were were gases at the sun. You had to do the experiments here first. So yeah, there's a lot of things get out of chronological order when you start talking about this stuff. But it does fall into place scientifically. But you asked a very good question. People did spectroscopy. And now we'll just go through the actual steps, because you got to understand, spectroscopy in the 19th century was done. This is and don't hold me to this geometry. This is just a quick sketch. You had a light source and a thin slit. And then you had some sort of dispersive element. Here's the prism. And some kind of optics to focus that slit onto a glass plate that had a photographic emulsion. Now, photography didn't come into existence until around 1830 or so. And you had to generally make your own emulsion, so you had to be a chemist as well as a physicist. And then you would take this exposed plate and carefully take it into the darkroom, where you would develop the plate doing your own chemistry, and then you'd fix it and you'd let it dry off, and you'd take it out and you would see probably some black body spectrum and probably some lines in the spectrum. If you were looking at a gas, let's say hydrogen or helium or something else. But those lines are actually images of the slit. And thus it became known that these were called lines. That's where the word spectral lines comes from, is that those images are images of the slit. The slit is like a line, so the word line comes into use in spectroscopy. Now, this experiment is fraught with potential disaster. First of all, you don't know what the spectral response of your emulsion is. You may not even know very well what the dispersion of that prism is. Or maybe even your optics. Your optics could screw you up too. You also don't know if you distort the emulsion while you're developing it. You're rubbing your hands over it, you're doing things. You don't know whether temperature change is going to mess that up when you're processing it and so on. So you're running some risk, but eventually you do get some measurements made. And you can take some measurements and learn some stuff. Well, Joseph Stefan, experimentally in 1879, and a little bit later, Boltzmann, using theoretical studies from thermodynamics, shows that the radiated power from a hot object is proportional to the fourth power of the temperature. This is the so-called Stefan-Boltzmann law, and it's obtained by Stefan experimentally, and Boltzmann put some theoretical backing to it, and it's obtained by making some spectral measurements and knowing what is a good range over which to measure the black body spectrum. Then in 1894, Wilhelm Wien measures the black body spectrum with his spectrometer, and he decides that the wavelength of the peak of the black body spectrum times the temperature of the black body is 2,898 micrometers Kelvin, and it's a constant. Okay? Seems pretty good. That's a nice rule. Except it doesn't work at long wavelengths or low temperatures. It seems to break down. And so it's a good rule for moderately okay temperatures. If these were incandescent bulbs, I would say like one of those bulbs, but they're not anymore. But anyway, this is a problem. It works pretty good in the region I showed you, the black body curves, but it doesn't work at very low temperatures or way out when the wavelength of the black body curve peak is at longer wavelengths. So the next thing that happens, meanwhile people are sitting around worrying about the Wien law not working, Rayleigh, with some corrections by Jeans, comes up with this interesting rule that says that the energy density of black body radiation per unit wavelength is proportional to the temperature divided by the fourth power of the wavelength. Now let's rephrase that a little bit. The wavelength is proportional to the inverse of the frequency. Okay, you agree with that? Which means that the energy density of black body radiation is proportional to the temperature times the frequency to the fourth power. So if you increase the frequency, meaning going to shorter and shorter wavelengths or higher and higher frequencies, you're going to get infinitely more radiated power. We know that doesn't happen. Otherwise, we'd be bathed in ultraviolet radiation all the time. That's called the ultraviolet catastrophe, and it's an incredible failure of the model. Once again, we find that classical physics breaks down. The experimental results are fine. Problem is, when you take it to the extreme, where you always can go, whenever you're making an argument in physics of any sort, in your own thesis work or anything else, to test out your ideas, carry it out to the extremes. If this measurement were made at a different wavelength, at the longest wavelength possible, the shortest wavelength, what would happen? That test your ideas in the extreme gives you a sense of whether it's right or wrong. And anyway, here, this very nice thing, which works fine in the general region of the visible, is a catastrophe when you go into the short wavelength region. So, what happens? 1900, Max Carl Ernst Ludwig, guy's got 4 first names. It's got to be important. A guy with 4 first names, he must be important. Planck. Fortunately, we only say Max Planck. Okay. He says in 1900 he proposes, and it turns out it's a completely empirical explanation, which simply means that he proposes his empirical explanation just because it works. He doesn't derive it from somewhere else. He proposes it because it works. And he does it in the face of Maxwell's brilliant electromagnetic radiation theory. You know, these waves that are called light interfere as waves, they diffract as waves, they propagate speed c. You know, that speed doesn't get invented. It falls out from the equations. They're polarized and they look, sound, and they probably smell like waves too. So Max Planck says, no, they're not waves, they're particles. And on the first day of the quantum mechanics revolution, which is in 1900, Planck says, instead of waves, let's think of light as being composed of particles. Particles having energy equal to some constant times the frequency, which is immediately a major problem. You understand that? You realize why it's a problem? Because it's the first day of the revolution and we already have a wave-particle duality problem. Frequency is a property of a wave. And yet Planck is saying that it's a particle. On the first day, you've got a particle that has wave properties. What does that mean? It's a conflict, and it's saying I'm going to choose to think of my wave as having particle properties because if I make that choice, I can explain the black body problem. I don't argue why I'm choosing it to be particles. I'm saying that if I choose that they are particles, I can explain the black body problem. I'm not saying why I'm making this choice. I'm saying by choosing it, I can solve the black body problem. A little bit later, Einstein is going to choose the particles to explain the photoelectric effect. and on it will go, and we will continue to have a wave-particle duality right up until the present. And there's some people that will argue you don't need particles to explain anything. You can explain all of optics, modern optics too, in terms of waves. I'm not going to argue with you on that, but there was a bet placed some years ago on whether you needed particles at all, and I don't really know what the outcome was, but it was a pretty famous bet. I think it involved my thesis advisor and a guy named Edward James. And again, I don't know who died first. The bet was never consummated. Anyway, so we have this duality from the very beginning. I want you to be aware of that because it's a change in thinking in the world of physics, which also leads to a change in the way the rest of the world sees science. All of a sudden, science is saying light is both wave-like and particle-like. It's a sort of a not too comfortable place to be. The world itself is not a too comfortable place to be. So science is heading out into a new subject, into a new concept, and it's not the most convenient and nice place to be. So when Planck does this, he says, assuming light is quantized, he can derive this famous black body spectrum, this thing over here. That the spectrum of the black body is this equation. Okay? You've all seen that. Brilliant piece of work. He didn't write it down that beautifully, but he came very close. And also, he didn't know the value of the Planck constant. He had numbers in there. And eventually, it got cleaned up to be 2 pi a, this constant a was 2 pi c squared h, and b was hc divided by Boltzmann's constant. And he got away with doing this without using a computer. He did it by hand, maybe with an ancient slide rule. Does anybody here know what a slide rule is besides me and Andrew?
Heard the word.
You've heard the word, you've never seen one. And maybe I'll bring one in sometime and let you see what we had to suffer with.
Yeah, we used one once, like a long time ago, like in high school.
You used one?
Yeah, but it was just to show us that this existed at some point. But I don't remember anymore how it works.
Okay, neither do I. I can't remember how to use it either, but I still have it. It's an antique. Anyway, he does this fitting without the aid of a computer, and he gets away with the 2 fitting parameters. And at first you think it's just one equation, but no. He takes the derivative of that of the equation, and then he can fit the derivative, which is giving him the peak wavelength. He can fit that to Wien's law. So he has 2 equations, 2 unknowns, A and B, and he can solve it. And it's a hard fitting to do, but he solves it. And then on October 19th, 1900, he presents it to the Berlin Physical Society, and the revolution begins. That's the beginning of the quantum mechanics revolution. All of a sudden, the world has to think of light coming in the form of particles. So if light comes in the form of particles, can it account for the line spectra of the atoms? It's been a problem for a long time, and as I said before, if you look at the sun spectrum with a spectrometer, you find a continuum with some missing lines. Later on, they're found to be the absorption features of different gases. If you look at the emission of the hydrogen discharge lamp, you see discrete spectra. You want to know what those do, what causes those. And all you have available to you at that time, in the late 19th century, is the oscillating dipole as a model for how the atoms radiate. What causes them to come out of a discharge lamp? You have an oscillating dipole. And the reason you got to keep in mind that this is all you got, because the electron had not been discovered yet. Okay, think about it. Nobody even knows that there are electrons. Certainly nobody knows that there are protons and neutrons. The neutron wasn't really discovered until the 1930s. And so, getting a little ahead of ourselves to look at this oscillating dipole, let's just think about the electron on a spring model, okay? Just a simple electron on a spring. And you make this model and you find out that you can't account for the line spectrum. Not only that, but the electron on the spring does not result in stable atoms. It results in atoms that decay and vanish, which is very bad because we know atoms are stable, and so the model doesn't work. So the classical electron on the spring, there are no lines and it's unstable. You know from electromagnetics that something that's an accelerating charge radiates, so the oscillating electron is radiating, and eventually it loses energy, and as it loses energy by radiating, it's going to crash into the nucleus. This is assuming, once again, getting ahead of where physics was, but just thinking about an oscillating dipole with some kind of negative and positive charges oscillating. And eventually the two will collide with each other because they'll radiate away the energy they've got. And when they do, there will be a collision. And as they do it, the spectrum will be continuous because the rate of oscillation, the rate of radiation will change as they get closer and closer together. They lose energy, but have less, they have less energy left. So as they get closer to get together, having less energy, they're radiating lower frequency until they collide. And classical physics then does not give you stable atoms, and it clearly can't give you line spectra. So the problem of classical physics is it doesn't have a model that works. It can't explain the facts that we have, line spectra, stable atoms, and what have you. So we want to first summarize the data, and then we'll try to construct a model that makes sense. The experiments and the data. Okay, you prepare atoms, not molecules. Atoms are much easier to work with. And then you perform precision spectroscopy. Photography is barely understood, as I pointed out. It only got invented around 1830. You probably made your own emulsions, and they probably weren't very sensitive over the spectral range that you wanted to work with. Certainly you didn't have CCDs or Polaroid film even. And then you had to do your own development with your homemade emulsions and your homemade chemicals and all that stuff that wasn't good to be around. And then if you haven't damaged them, you had to measure the distances with some precision. And way back in the olden days, you took your glass plate and you put it down on something called a scanning densitometer. That was like a lathe, a milling machine with a microscope on top of it, and some focusing optics and a light source that would scan along very fine motion, measuring the distance between the lines on your plate, recording that information and telling you with some precision that was there. But early on, you didn't have one of those. You more or less took a ruler and you measured the distance between these lines, and you gave results. And if you trusted your calibrations, you could report on the wavelengths that were there. Okay, so now, what happens? Here's where science gets rather interesting. In 1885, Johann Jakob Balmer is a school teacher in Basel, Switzerland. He is not a physicist. He has no other claim to a role in the world of science. Never again does this guy do anything related to the future of science. But he does something that's incredibly important, and he will never be forgotten, because he was a numerologist. He liked to play with numbers. It took him 17 years from seeing Angstrom's measured values for the 4 lines of hydrogen until he realized that those 4 lines could be represented as 364.5 nanometers, actually 0.50682. He didn't give it in that precision, but that's the number today. But he realizes it's 364.5 times 9/5 times 4/3 times 25 over 21 times 9/8. Isn't that incredible? This guy sits around for 18 years, 17 years, what is it, 18 years? 17 years, he sits around, stares at those numbers, finally the lights go off in his head, and he realizes not only is it given by these things, but that those fractions are 9/5, 16/12, 25/21, and 36/32. And even more spectacular, the numerators are 3 squared, 4 squared, 5 squared, and 6 squared. And the denominators are 3 squared minus 2 squared, 4 squared minus 2 squared, 5 squared minus 2 squared, and 6 squared minus 2 squared. Wow! This guy has done something remarkable. And finally, he could say the wavelength is h times m squared over m squared minus 2 squared. Something phenomenal just happened. Balmer has said the properties of the hydrogen atom are determined by integers. Do you realize what an incredible leap into the subject of physics has just been made by a guy who's got no training as a physicist? He's a numerologist. He presents a paper at the Scientific Society of Basel, and that's it. You never hear of him again. Now, let me ask you a question. He says the series ends when m gets to be 3, because if m gets to be 2, you have an infinity here. But what happens as m gets very large?
Reduces to 1.
Hmm?
The fraction reduces to 1.
Yeah, but what's the difference between m very large and m minus 1 very large? Very small differences,
Yeah.
which means that fuzziness that I showed you in the picture,
Goes continuous.
it begins to look like a continuum. There's very little difference. So you have, for small values of m, you have lines spacing, and for large values of m, they get so close together that you can't tell them from a continuum except for very high resolution measurements. So he's telling you that that he can explain what you've seen. And he's saying, it's integers, guys. Start looking at integers. Well, since he's not a physicist, you don't know who's going to listen to him. But the implications are earth-shaking. Hydrogen atom is emitting light with wavelengths related by integers. So this numerologist has suddenly pointed physics in a new direction. And it's clear that integers matter. Rydberg claims he'd been doing this for years, long before Balmer ever said anything. Of course, if he had been doing it, you would have hoped he'd say something about it. It might have been sour grapes, we really will never know, but Rydberg's work was much more thorough than Balmer's and greatly expanded the utility of the idea that integers matter in the spectra of various atoms. And so Rydberg has a very important place in the history of science. Well, the formula works, okay, Balmer's formula, and it's applied in other series, not just the Balmer series, but the Lyman series and other series in various atoms and even molecules. So the situation that we find ourselves in after Balmer gives his paper in Basel is very similar, if you think about it for a moment, to where classical science was, classical mechanics, to the time when Copernicus puts forth his model for the Earth going around the sun. Brahe has all his data from observing the moons, the stars, whatever else. Kepler looks at Brahe's data and comes up with Kepler's laws of motion. And Galileo's concepts and observation of the moons around Jupiter. What was missing at this point in the quantum mechanics revolution is the synthesis. Just like Newton, the synthesis wasn't there yet. And it wasn't there because we hadn't discovered the electron yet. Okay? And that comes from J.J. Thomson and a few other people making contributions. Well, with the discovery of the electron, you still have the problem of classical physics that the electron charged object that Thomson had found by scattering experiments is going to spiral in, and as it does that, it's going to radiate continually and eventually crash in to whatever it is that's positive in the atom, because the atom has no net charge, and the atom would still not be stable. So either something was wrong with the scattering experiments that is not so, or the models were wrong. And something was very wrong with classical physics when you're looking at the scale of atoms. No one argues with classical physics in the human-sized world, or even in the little child-sized world, but in the scale of the atoms, there's a problem. And so we come to Niels Bohr, whose work actually puts quantum mechanics on the road to becoming a full-fledged, meaningful, and incredibly precise science with incredibly accurate predictions that are incredibly proven in experiments. Everything that's been predicted is measured. Everything, somebody goes out and makes a measurement, and sure enough, quantum mechanics predicts it right on to the 6 or 7, actually 8 decimal places nowadays. So in 1912, Bohr goes to work at J.J. Thomson's lab as a postdoc for about half a year when Thomson throws him out. And that's because Bohr did not agree with Thomson's model of the atom. And I wrote it down there, the plum pudding model, which is the idea that the atom is kind of a blob of stuff, that the electrons moving around in this blob of stuff any way they wish. And somewhere inside the blob, there's something that's positive, so to keep the atom neutral in net charge. But in that model, the electron can move around and radiate continuously. It can't give rise to stable states or line spectra. It's still got a lot of problems. And Bohr is quite convinced that this is the wrong model, and he keeps telling Thomson this, and Thomson finally says, I can't stand it anymore, you have to go. And Bohr leaves and lands in Rutherford's lab at Manchester University, where Rutherford is in the midst of developing the planetary model of the atom, in which there's a positively charged nucleus. He doesn't know what it's made of yet, but it's positively charged. And the electrons orbit around it as they would if they were little planets going around in orbits. And Bohr says, aha, this is good. I can think of these electrons orbiting around the nucleus, and it will help me to understand why there are stable states and what kind of transitions those stable states make. And it might just help with understanding things. So it also, when Bohr's work finally comes out, it leads to the general acceptance of Rutherford's planetary model of the atom, which helps Rutherford get his Nobel Prize as well as Bohr getting his. So while Planck introduced the concept of quanta to electromagnetic energy, Bohr is going to effectively introduce quanta to matter. He's basically going to quantize the electrons and the nucleus and all of that stuff. He's going to introduce quantum states of matter in his model, which is again another one of these difficult things to accept when we've been doing it so differently before. we sort of had in mind quanta of charge when thinking about charged particles in the past, but now he's given them what we'll see are quantized states of existence. And there's always this difficult problem is why should something so odd be intrinsically a part of nature? Okay? Why is nature organized in integers? It doesn't make a lot of sense, but in fact it turns out to be so. You have Balmer's results, it tells you it's so. You have Rydberg's results, it tells you it's so. So Bohr says, and in what is now what we'll call the zeroth order picture of how an atom works, he says something that, if you stop and think about it, is totally obvious. Okay? He makes the statement that atoms have stable states. Completely obvious statement. We know they don't decay away, so they have stable states. And then he says that and here's where Bohr's brilliance comes in. He says that the atom in a stable state stays there unless it absorbs or emits electromagnetic radiation. And when it does absorb or emit electromagnetic radiation, the amount of energy that it absorbs or emits has to be exactly equal to the amount that causes the atom to change to another stable state with exactly that much energy. So it can absorb one of Planck's photons and go up, or if it's up there, it can emit one of Planck's photons and go down. That's the essence of Bohr's thinking. But from that comes an amazing understanding. The states have energies described by integers. Bohr will start counting the states available to the atoms. There's not a continuum of those states. The large M number states are just very closely spaced as Bohr constructs his model. He can explain Balmer's high order or almost continuum states by just having the difference in energy between En and En plus 1 being very small. And on he goes. He can construct an explanation just by assuming the states are stable and have integer values. So he builds in quantization of the states of atoms. And thus he quantizes the atoms, and he gets it by demanding that the states have energies described by integers. You see how radical that is? Today it doesn't sound very radical at all. But in that time, it was incredibly radical. In that time, he was telling the world of science, you let Max Planck do it for the photon, for the electromagnetic waves. If you let that happen for the states of the atom, now I can tell you why you get line spectra. And I can tell you why discrete lines eventually begin to look like a continuum, because the states are very close together at very high quantum states. And I can do all of this by just assuming that atoms have stable states and they're described by integers. So, what he has done is not only show us a powerful tool, but he's also taken away the chance that the electron will spiral in and collide with the nucleus. He doesn't know there's a nucleus yet, he just knows that there's a positive charge somewhere to take up and keep the atom neutral. It prevents the electron spiraling in, reaching hyperrelativistic speeds, and crashing into the nucleus and causing disaster, because hyperrelativistic speeds are no good. You know, Einstein said you can't go faster than the speed of light and all that sort of stuff. So it gets you away from the classical planetary model. In the classical planetary model without stable states, in the Rutherford model, without the stable states, it still crashes into the nucleus. So he's given modern theorists the tool of quantization to remove singularities. These infinities are not there anymore. Now, it will take many years to remove all the singularities that are encountered, because at this point nobody knows when they're going to be found. And today, that's the problem with quantizing gravity, is that trying to remove the singularities has proven to be very, very difficult. The gravity problem is so very well solved by general relativity that even though it gives singularities, for example, at the center of a black hole, general relativity is very, very hard to quantize. But this technique has been absolutely superb in all other cases. So Bohr has provided a fantastic tool in addition to explaining the properties of atoms. Now, he hasn't provided the kinds of mathematical tools that will come up in the future. So we're going to look in the future next time, which is after next week. Next week is spring break, as I recall. So the week after that, we will go into the planetary model problem. We'll look at Bohr's model in more depth. We will see that Bohr's derivation of the Rydberg constant was crucial to the acceptance of quantum mechanics. In other words, so far we've just said what the model was, but one of the things that comes out of Bohr's model is a derivation of a constant that Rydberg put forward. And Bohr's model enables you to derive Rydberg's constant from fundamental properties like the speed of light, mass of the electron, charge of the electron, whatever. And we're going to look quite carefully at something called the correspondence principle and discuss quantized angular momentum and spin, and look at de Broglie's particle waves. Now we're going to have quantized particles, and they will have wave properties too. So we're going to begin to see science, physics coming around in both ways, and we'll also preview the third part. And after the third part, we'll get together and see the play Copenhagen. Okay? So I thank you. Are there any more questions or comments? I've been so clear that nobody can
So much.
Huh?
So much.
So much. So much. I know it goes on. There's just so much happening at this point. And you know, the way we teach the subject in classes, we teach it without the context and the order of things, the way things happen. You don't realize that Bohr did his work as a postdoc. Yeah.
When was this all? When was this all in reference to the Millikan oil drop experiment? I don't remember what year that was.
The Millikan oil drop experiment was later.
It's like the 30s.
I don't know about the 30s, but it was certainly later than these events. So the value of the electron charge was not known.
Or the, yeah.
MJ is going to see everyone. 1909?
Yeah.
Okay. So, yeah, it was around that time.
Which experiment determined the mass? I can't remember that.
The electrons?
The digital mass of the electron, yeah.
Once you know the charge, you can do
Oh, yeah,
electron
then you got
mass.
both, basically.
You can get both.
I did that experiment as an undergraduate.
Okay.
A little chamber with
With a magnet. Yeah. We probably all,
back to the roots out.
yeah, the oil drop experiment is a difficult one. When I was a graduate student, I shared a lab with a fellow who was doing a version of the oil drop experiment. He was making superconducting niobium balls float in a magnetic field, and with ultra high precision trying to measure the way they would move, and seeing if the electron charge differed from whatever value it had in some very high degree of accuracy, precision, because my advisor, who was his advisor, had this notion that he could explain the expansion of the universe by a charge imbalance, just by Coulomb expansion. Yeah. He didn't. He just got a better value of the charge of the electron. Yes.
Just as a matter of how time is really kind of compressed, I know I'm no guy, but also as an undergraduate, I did astronomy labs. And the astronomy labs, we didn't make our own emulsions. We had the plates with the emulsion. What we had in the lab was to go through and do a series of exposures and with different development conditions, different developer temperature, in order to calibrate the plates, because most astronomy was done in the 1960s with photographic plates. There were PM photomultiplied tubes on the end of telescopes that would be used for very, very faint objects, but everything else was photographic plates. And if you want a really boring experiment, because you had to do it in absolute darkness, it's sensory deprivation to sit there for 15 minutes, for a half hour, for an hour, agitating the plates, because they had put new developer on all the time, with absolutely no light. Anyway, back in the days of wooden ships and iron men.
Yeah, I can sympathize with that. The first experiment I ever did was optical sum frequency generation, and that involved exposing a photographic plate in a Hilger and Watts prism spectrometer, and then rushing off to the darkroom to see whether we got 1 omega, 2 omega 1, 2 omega 2, and omega 1 plus omega 2. And it took weeks till we had everything aimed properly, and sure enough, one day it was there.
And the most famous experiment with the photographic plate done by my grandfather and your father, right? You can tell the story.
Yeah. Oh yes. The most amazing experiment screw up that ever happened. Peter Franken had the notion, once a laser was available, that you would have a large. First, back up a step to James Clerk Maxwell. He wrote down that the response of the medium would be proportional, would be written as a Taylor expansion in the powers of the electric field. So you have, as was shown in the seminar last week, a first order term, second order term, and so on, and Maxwell threw away all but the first order terms. Franken said, no, the second order term will be there because now we have high fields with the lasers, and Weinreich pointed out that you had to have a non-central symmetric material to get the second order term to be there. And they found an undergraduate who was quite creative in doing experiments because there were no graduate students available. I was still in my first semester of graduate school when we started this. So they took exposures many times using a piece of crystalline quartz to try to see the second harmonic. If you're going to see second harmonic of ruby, which is at 3,400 or so nanometers, 3,400 angstroms, you would have to have something that not only was non-central symmetric, it had to transmit the 3,400 angstroms. So crystalline quartz was a good choice. So then finally they did see it. They developed it, they prepared it for physical review letters. They sent it off to physical review letters, and the man setting the type for the article saw this little fuzziness on the screen where the arrow was pointing 3,400 nanometers or whatever it was, and he airbrushed out the little fuzziness because he thought it was a fault in the plate. And so the first article on second harmonic generation appeared with an arrow pointing to nothing. But everyone in the whole community knew exactly what it was, and the floodgates opened. Anyone who wanted to do something with a laser jumped into nonlinear optics. at that point. It was the spring of 1961. And,
How many months after Lyman,
hmm?
how many months after the first Ruby laser was functional was this experiment? How did he get a hold of it so quickly?
That's a very interesting question. The first Ruby laser was operated around the middle of May 1960. The reports of it were out in June of 1960. A commercial version of that laser was available. Well, I'm going to show you this experiment later on in the course. The first laser was available commercially in late fall of 1960 by a company in Ann Arbor, Michigan. And so Peter Franken was able to shift some money around in a grant that he had and buy such a laser, and was doing the second harmonic generation in the spring of 1961. I'll tell you a little personal story. I started graduate school in the fall of 1960, and he told me, he was the graduate student advisor, and I had, I'll brag a little bit, I had done very well in that first semester. He suggested I look around for some thesis work to do. And I'd done all the usual looking around, and I'd stumbled into the lab where this Alan Hill, the undergraduate, was using the Ruby laser, and I said to myself, my God, anything that can make that much light has to be worth studying. So I offered Franken a deal. If he would promise that I could work on the laser, I would be his student and work on the laser. Next thing I know, it's now, when 60 years later, I'm still doing it. So, actually, not 60, 55 years later. But anyway, it's a career.
So that laser could have been prototype like 3, or serial number 3 from that company.
Yeah, probably. Well, the interesting point is that Maimon's laser, as you're going to see when we get there, is extraordinarily simple.
Yes.
And it's amazing how other people in other places tried to make it complicated. And the result was only a few people got their hands on a Maimon version of the laser. Not long after that time, better kinds of lasers came out, and it was no longer really necessary to use a Maimon type laser. There were better ones, better lasers became available. But still, to get started, the Maimon type laser was a great way to go.